Welcome back to module 4. We are briefly reviewing matrix algebra, and next we will understand complex conjugate of a matrix. Complex conjugate of a matrix will be given by taking the complex conjugate of every element, which means that if I have a matrix like this A1, A2, A3, this is a column matrix which is a vector, then A star is going to be making complex conjugate of each element. Adjoint of a matrix, it is similar to transpose. It is similar to transpose, but elements are replaced by its complex conjugate. Which means that I have now Ij. If I use adjoint, if we find out adjoint, adjoint is defined by this dagger sign. Adjoint is going to be A J I star. So, I am interchanging the row and column. At the same time, each element will be will be taken to be complex conjugate. So, let us say I have a function a matrix like this 1 I 2 I, then adjoint of that matrix would be, first of all we will change the row and column and then we will take the complex conjugate. 1 is real, so there is no difference. I would be minus I now and 2I would be minus 2I. When A equals A dagger, that we have already seen, when an operator is equivalent to equal to its own adjoint, it is called Hermitian operator or Hermitian matrix in this case. An operator will be expressed in terms of matrix. So, the name can be interchanged depending on the usage. So, we will have Hermitian, this is called Hermitian operator, Hermitian matrix, right now we will call it matrix. Hermitian matrix is defined when it's adjoint, when it becomes self adjoint. We will look at vector dot product. Generally, algebraic definition of vector, a vector is represented like this way in algebra: Ax plus j Ay plus k Az. I, j, k with cap, they are representing the unit vector along that x, y, z axis. This is x, this is y, this is z. So, unit vector is going to be I cap, j cap, k cap. So, if we do that and then b vector, another vector can be represented by bx plus by plus bz. Here we are representing the vectors with the help of I, j, k basis. And algebraic definition of dot product. So, we can take the dot product as A dot B, which is given by Ax Bx plus Ay By plus Az Bz It's because I dot I would be, I dot I would exist, it will be 1, but I dot j or I dot k, they are all 0. So, that is why, because they are perpendicular, it becomes cos theta. So, I dot I is nothing but 1 multiplied by 1 multiplied by cos theta. Cos theta is going to be 90 degree, because this angle is 90 degree. So, we get 1. So, this is the definition comes from algebra, and in the matrix form, if I want to represent it, as I have told you before, that this vector can be represented in the matrix form. When I represent the vector in matrix form, it becomes a column matrix Ax, Ay, Az, and B becomes a column matrix also Bx, By, Bz. These are represented with respect to this basis. Often we do not mention that one. Implicitly we say we keep it we keep it hidden in when we are describing the matrix representation of the of a vector, assuming that we know what kind of basis we are using, but we have to remember that the actual terminology or actual construct of the statement should be following. This vector A and B has been represented with using these column matrices with respect to this particular basis. If we change the basis, the value of each element will change. So let us see what does it mean by this dot product. If we do the dot product, it means that I have to first, so dot product, I have to reach this value, this expression. Finally, I have to reach this expression, and this expression can be obtained by taking like this way. A dot B, when I say A dot B in the vectorial notation, this is equivalent to A dagger multiplied by B. This is the matrix representation, A dagger B, and A dagger is the adjoint of A. Adjoint of A is going to be Ax star, Ay star, Az star multiplied by Bx, By, Bz. In the end, what I get? Ax star Bx plus Ay star By plus Az star Bz, and that is the definition of the dot product of two matrices, which you get here is equivalent expression. So, dot product has to be done like this way in the matrix form, and length of the vector is called norm of the vector, and norm is represented by following. The norm is actually length of the vector and that is represented by, it is actually, this is representation of the vectorial representation. Then we will go for matrix representation. Matrix representation is going to be A dagger B to the power half. That is the norm, which is nothing but square root of Ax square plus Ay square plus Az square. That is the way the norm would be represented in the matrix form. This is the matrix form of the norm. So, we will now move to inner and outer product. We will erase this part to make some space. Inner product a column matrix, before we represent the inner product, a column matrix represents a vector. I have already mentioned that one, and if I use Dirac's bracket notation, it is not bracket. The C is missing here. It is called bracket notation, but the meaning is similar. In the bracket notation, Dirac notation, this A, the column matrix, is represented by this notation. It is nothing but A1, A2, A3 like this. And adjoint is represented by, so this is Kate notation, this is Kate notation, and this is now bra notation, and that is nothing but in the matrix form it is the adjoint of it, which means it is A1 star, A2 star, A3 star like this. It becomes a row matrix. So, this is represented by a row matrix. And when I say inner product, it is the bracket notation. So, I use this bracket notation. I do not have C. In bracket notation, inner product will be given by like this, which is nothing but in the matrix form it is going to be transpose, it is going to be adjoint multiplied by its own. So, which is nothing but A1 star, A2 star, A3 star. Let us assume that I have 3 elements, then A1, A2, A3. I multiply, I get A1 square plus A2 square plus A3 square. And norm is given by square root of this inner product. The square root of inner product, I get the norm. Similarly, this is called inner product we are representing. So, this is inner product. Similarly, I can define outer product as well, and outer product is going to be following. I will have in this case I will not have bracket, I will have ket bra. So, outer product is given by ket bra, which means I have this multiplied by this. In matrix form, this is the Dirac notation. And in the matrix form now, I can represent it like this is going to be A matrix multiplied by now A dagger, which is nothing but A1, A2, A3, and this is going to be column row matrix. So, it is going to be A1 star, A2 star, A3 star, and if I multiply, matrix multiplication we have to employ, and matrix multiplication can be done following way. We have to always follow this way and this way. So, if we do that, then in the end we get this matrix A1, A1 star, A1, A2 star, A1, A3 star. So, we have to multiply this one first and this one, then I am supposed to add this one, next one multiplied by next one, but that is 0, we do not have anything. That is why we are getting only one term in this each element. So, I have to multiply this one first to get this element. Then I have to multiply this one first and this one first to get this element, and that is the way we will move forward. Similarly, A2, A1 star, then A2, A2 star, then A2, A3 star, A3, A1 star, A3, A2 star, and A3, A3 star. This is what we get, and after we get that, we can further rewrite this matrix as this one is nothing but this one and this one. All these diagonal elements can be represented by this, then A1, A2 star, A1, A3 star, similarly A2, A1 star, then A2, and then A2, A3 star, then A3, A1 star, A3, A2 star, A3, A3 absolute square. Okay. So, what we see is that in the diagonal term we get individual absolute square, and in the off diagonal terms, all these off diagonal terms, we get the cross terms. So, this kind of Ket-Bra notation will be used to represent the density operator. We will go back, we will come back to density operator later stage, not right now. It is related to density operator. We will come back to this later, but inner product, we have understood inner product is going to be bracket where I have presented like this way. We will move on, we will present the trace of a square matrix. Trace of a square matrix is the sum of all of its diagonal elements. Which means that I will write down TR within bracket A is nothing but summation of A I. So, if I have a matrix like A11, A12, A21, A22, then trace of A would be, A11 plus A22. Its diagonal elements we have to sum. Determinant of a square matrix, if I have a matrix like this, A11, A12, A21, A22, then determinant is given by, is represented by this, is given by this A11, A12, A21, A22, which can be simplified as A1, A22 minus A21, A12. This is called determinant of the square matrix. Inverse of a square matrix, if matrix looks like this, A11, A12, A21, A22, then inverse of the matrix would be given by, will be defined as, this will be defined by A inverse. If I matrix multiply A inverse, that will give me an identity matrix. An identity matrix, what is identity matrix? Identity matrix is nothing but the diagonal element is 1. That is the way inverse of the matrix will be defined. We will move on and we will explore now the eigenvalue and eigenvector of a square matrix. This is an important subject and in linear algebra, and this is used very frequently to find out the eigenvalue and eigenvector of the Hamiltonian operator. And Hamiltonian operator will be represented in terms of square matrix, and the moment we represent it in terms of square matrix, we will be able to find out eigenvalue and eigenvector. Eigenvectors are eigenstates, so which means that I will be able to get the different eigenstates or the spectrum of the system. So, this subject is very important. The eigenvalues of a matrix can be computed from using this characteristic equation of the matrix. This is called characteristic equation. And this is identity. Identity matrix or unit matrix I, and this is zero matrix or null matrix where all elements are 0. So, we'll do one thing, we'll take one example here to find out eigenvalue eigenvector. So, let us say I have the matrix 2 1 1 2, a simple 2 by 2 matrix I have. So, if I have 2 by 2 matrix like this, then characteristic equation would be following. It is going to be determinant of 2 minus lambda 1 1 2 minus lambda. This is the characteristic equation. Why it is so? Because A is 2 1 1 2 minus lambda multiplied by identity matrix or unit matrix, which is given by 1 0 0 1, then its determinant. So, addition or subtraction. So, first of all, this is a scalar multiplication. So, we will be able to multiply each element with this scalar. Once we are done, then we can use this subtraction. Subtraction is equivalent to the addition procedure, where each element will be subtracted, which means that I will be able to get matrix 2 minus lambda, then 1 1, then 2 minus lambda, and we are taking the determinant. So, that is exactly what we have written here. This is going to be 0. So, this is actually what we have written here. This determinant has to be 0. I will get a 0 matrix. So, these values will be 0. So, how can I get that? The determinant can be simplified as follows: 2 minus lambda whole square minus 1 equals 0, or lambda square minus 4 lambda plus 3 equals 0, or I can write down lambda plus minus 2 values I will get, because some order is 2, second order. So, I will be able to get 2 values, which is going to be 4 plus minus square root of 16 minus 12 divided by 2. That is the root finding. We are trying to find out the root with the general expression, and I get finally the value is going to be 3 and 1. So, lambda has now 3 and 1. And what is lambda? Lambda is the eigenvalue. Lambda is the eigenvalue, which means that if I have an Hamiltonian operator which is represented now in terms of Hamiltonian matrix, once we represent it in terms of Hamiltonian matrix, then I can find out just like this way. We will not follow this procedure. There are other more convenient procedures are available, not using this characteristic equation. I will present it what kind of convenient procedures are available. But let us say I have certain convenient procedure to get the eigenvalues. Once I get the eigenvalues, it means that I am getting all the energy levels. Here, because it is 2 by 2, I get only 2 energy, 2 values of the 2 eigenvalues. Next, we would like to find out for lambda equals 1, what is the associated with particular state lambda equals 1 eigenvalue, what is the eigenvector or the wave function should look like. That can be represented by following. We have this eigenvalue equation, which is A wave function equals lambda wave function. That is the eigenvalue equation. And in the matrix form, how do I represent it? In the matrix form, we will represent it. A has been represented in terms of matrix 2 1 1 2. Then psi is going to be unknown. It is unknown to me. That is why I will write down A1 A2. Remember, I am now representing psi in the basis of something whose and that basis is giving me this coefficient, just like the way we have presented previously. So, these coefficients are with respect to certain basis. Let us say the coefficients are A1 and A2, and which means that lambda equals 1 and then A1 A2. A1 A2 is unknown. So, psi, this wave function associated with this particular eigenvalue, I am representing like this A1 and A2, a column matrix. So, I can now multiply vector, this is matrix multiplication, and this matrix multiplication will give me 2A1 plus A2, and another one is A1 plus 2A2. This is the matrix I will get, which is equals to A1 A2. So, now what we will do? We will equate the components of the vector on the left and right hand side. If we equate it, so this part has to be equal to this and this part has to be equal to this. If it is so, then I will be able to write down 2A1 plus A2 equals A1, or A1 equals minus A2. So, if I have A1 equals minus A2, I can assume that okay, A1, let us take A1 to be 1, because does not matter what basis we take, finally we need the relative components. So, for a particular basis I may get A1 equals 1, and if I get A1 equals 1, immediately I get A2 equals minus 1, which means I have the wave function associated with this state, that particular eigenstate will be represented by 1 minus 1. One can suggest, okay, I do not want to use 1, I want to use 2, and then I can get 2 also, minus 2, that is also fine, one can use that. It does not matter what we use, because depending on the moment we take 2, it means that I am changing the basis. Depending on the basis, I may get different coefficient. So, I am selecting one basis for which I should get 1 for A1, and the moment I get 1 for A1, I get 1 minus 1 for A2 immediately, and we can represent that wave function by this way, 1 minus 1. So, 1 minus 1 is going to be the representation, and I have 2 states. So, I have 2 states like this. One state I have given is lambda equals 1, another one is 3, and this wave function will be represented 1 minus 1, and we will see what is the representation for this. So, for that we have to take lambda equals 3. So, here we have to take 3, lambda equals 3, and if we take lambda equals 3, then this is going to be 3, and if it is 3, then again we can use the matrix multiplication rule. It takes quite a while to be familiar with this matrix multiplication part. So, I suggest you to practice a lot. 2a1 plus b2 sorry, this now going to be our new coefficient, because this is a new state. So, I will call it b1 b2, and this is b1 b2 associated with this eigenstate. So, I have this 2 b1 plus b2, and this one is b1 plus 2 b2, which is now going to be 3 b1 3 b2. So, now I have to equate this each element on both sides. If I make them equal, then I get 2 b1 plus b2 equals 3 b1, which means b1 equals b2. In this case, now if I use b1 equals 1, then b2 equals going to be 1. So, I have now the second state to be like 1 1. That is the state we have. So, if A is represented by the Hamiltonian, then I have two states, and for these two states the first energy is going to be 1, second energy is going to be 3, some unit, and each wave function associated with these states will be represented by this column matrix 1 minus 1 and 1 1. We will use heavily use this kind of matrix representation in this course. So, going over this exercise would help adapt the procedure. So, now what we will do, we will find out the norm of the norm of the eigenvectors. So, we have two states right now, and we would like to normalize both states so that we can get the normalized wave functions, and associated with this 1 minus 1 state we will get the norm. How do we get the norm? Norm is given by inner product square root of the inner product. Inner product is nothing but A dagger multiplied by A, which is nothing but 1 minus 1 1 minus 1 square root of this. So, square root of the entire thing. So, I get 1 plus 1 square root is going to be square root of 2. So, normalization constant is going to be 1 by normalized wave function is given by the psi 1, I call it, divided by its norm psi 1, that is we have shown already. So, this is nothing but 1 by square root of 2, then 1 minus 1, which is nothing but 1 by square root of 2 minus 1 by square root of 2. So, this is the normalized wave function we have associated with lambda equals 1. Next, we will normalize the second state, and the second state can be normalized in following way. We can again take the inner product, which is second state is 1 1 1 1 state, and if I take the inner product, we will see that again I have this is going to be the inner product is going to be again square root of 2, and that is why this normalized function psi 3 is represented by 1 by square root of 2 1 by square root of 2. So, these are the two, this is the representation of psi 1 and psi 3. Psi 3 has energy or lambda eigenvalue 3 and psi 1 has lambda equals 1. So, these are the two states we can represent with the help of matrix representation. So, one thing is clear from this entire exercise, that as long as we know Hamiltonian operator and as long as we can convert it to its matrix form, the moment we get the matrix form, I can immediately calculate its find out its eigenvalue and eigenvectors, and we can get normalized wave functions associated with that Hamiltonian. So, normalized wave functions and eigenstates are giving the quantum states for the system. So, finding out this eigenvalue eigenvector procedure is very important, but often we will avoid this using characteristic equation of the matrix. This procedure is rigorous procedure and it may not be useful for bigger matrix. The more convenient way of doing is diagonalization of a normalized matrix. So, it's a diagonalization of a square matrix. This is what we do. And what is diagonalization? I'll explain it right now. We have seen that if I take this matrix, this is just an example. We are illustrating this example so that we can understand it. For this matrix, we have seen that the eigenvalue is 1 and 3 and corresponding normalized eigenvectors are like this. We will stop here and we will continue the discussion of diagonalizing of a square matrix in the next session.